Okay, good evening and welcome to this problem solving session for the course on STOF systems. I'll start the today's problem solving session. So these problems will be related to the STOF systems, the response of the STOF system subjected to pulses and arbitrary forces. This is basically related to the weeks 4 content that is released in the um, website. Let's start the problem solving session. So the first problem is on a spring mass system with mass 80 kg. So the first problem is on this a spring mass system with mass 80 kg and stiffness 12,000 Newton per meter is subjected to a triangular pulse as shown in the figure. Let me draw the figure. So it's actually a symmetrical triangular pulse. So the magnitude is 15 Newton and it's acting for a duration of 0.1 seconds. So we are asked to find the natural period, impulse magnitude, maximum displacement of the system and equivalent static force. So in this thing, the first thing is related to the natural period. So that just depends upon the properties of the system, which is nothing but mass and stiffness. Those two properties are already given in the question. So we just have to find out Tn. Tn is equal to 2 pi by omega n, which is 2 pi divided by square root of k by m. So this would be 2 pi root m by k. So 2 pi square root of 80 divided by 12,000. Please try to solve the problems along with me so that if you get any doubts in between, we can discuss. So what is the value of natural time period that you are obtaining? So you would get a value of 0.51 seconds. So this is the first part of the problem. And the second thing is impulse magnitude. So, so when the impulse is acting for a very short duration of time relative to the natural period, then we can approximate this thing um, as an impulse acting for a very short duration, and the magnitude of the impulse will be equal to the area under this pulse diagram. So that concept is already covered in the lectures. So the impulse magnitude would be equal to the area of this triangle. So how much is this? 2.5 Newton second. So part C is related to the maximum displacement of the system. So for this thing also we will just use the approximate analysis, that is when the duration of the pulse is Td is equal to 0.1 second. So when this duration is less than Tn by 4, so in our case Tn by 4 would be 0.51 divided by 4, that would be, so this is 0.1275. So the duration of our pulse is very small. So in this case, we have a formula for the maximum displacement for the triangular pulse. So that is U max is equal to U static multiplied by pi Td by Tn. And what is UST 0? UST naught is P naught by K. So here P naught is 50 Newton and K is 12,000 Newton per meter. So this would be how much? So you would get 4.167 multiplied by 10 power minus 3. So we just have to substitute in the Umax formula to get the maximum displacement. So Umax is equal to 4.167 multiplied by 10 power minus 3. Td is 0.1 seconds and Tn is 0.51.
And what would we do if TD was less than TN by 4?
So then we have to go for exact analysis. So we know how to find the response for a impulse, right? So basically we have to divide the total response into two parts. So first is the response to the forced vibration that we can find out using the Duhamel's integral, because in this case we have the mathematical expression for this triangular pulse. So we can write out this triangular pulse in a mathematical form, like two straight lines. One is this part and then other one is this part. So once we get that response using the Duhamel's integral, so at the end of these things, we will have the initial conditions from the forced vibration response at zero point 0.1 seconds. So that will act the initial conditions for the remaining free vibration case. So that we can substitute in the free vibration response that we already know. So we have two components of response, and then we need to see which is going to be the maximum. So in the two things.
Okay.
Yeah. So what is a Umax? Umax is 2.567 into 10 power minus 3. So all the units are in meters. So this is meters or 2.56 mm. This is the maximum displacement for this SDOF system. And the last part is equivalent static force. So that means the maximum static force that would occur is because of this displacement, that is nothing but maximum force is equal to K effective multiplied by U max. So this is the maximum force that will be generated. So this is equal to 12,000 multiplied by this 2.567 into 10 power minus 3. So this is 30.8 Newton. Okay, this is a simple problem. So by knowing the formulas, we can substitute and then we can find out the different parts. Okay, we'll go to the next problem. So in this problem, an elevated storage has a mass of 1000 kg and height of 6 meters. The supporting structure has an effective stiffness of 600,000 Newton per meter. If the peak displacement response of the structure during an earthquake is 10 centimeters, calculate the shear force and the moment at the base of the structure. How would you solve this problem? So they have given the peak displacement as well of the structure. They want us to find out they have also given the effective stiffness and mass and everything. They want us to find out the shear force and the moment at the base of the structure.
We- We'll calculate first force, that is force equal to stiffness into displacement.
Okay, that would be the shear force. Yeah.
Yeah, and then
And then moment will be nothing but the overturning moment. That would be moment about the base. Since we already know the height, that would be the that would be okay. Let's try to solve this problem. So shear force is equal to uh, they have given 10 centimeters. So you should convert this into meters. Try to find the response and tell me the answer that you're getting. So shear force is equal to K effective multiplied by the displacement. So which is 0.1 meters. So it is
6,000 Newton.
okay. No, the effective stiffness is 600,000 Newton per meter or else 600 kilonewton multiplied by zero point 0.1 meters. So this would be 60, yeah, 60,000. So this
6,000.
is 60 kilonewton. The shear force is 60 kilonewton. So now the base moment would be the height multiplied by this force, right?
360 kilonewton meter.
Yes, 360 kilonewton meter. So now let's see problem 3. So we have a portal frame which uh, which has two columns of unequal heights because it's located on a sloping ground. Now we need to determine the following things. Determine the effective horizontal stiffness of the structure. So they have given the flexural rigidity values, lengths, they have given, and we need to find out the effective horizontal stiffness. So for this thing, we need to use the concept of static condensation, and using the response spectrum shown below, determine the following: total base shear, shear at the base of the short and long columns. So they have given a response spectrum. Response spectrum is nothing but response like in terms of either displacement, velocity or acceleration with respect to when we vary the time period of a single degree of freedom system. So for example, we have some ground motion from some arbitrary ground motion is there. So for that arbitrary ground motion, when it is applied to single degree of freedom systems of various time periods, we get certain response. So we plot that response, that is called as the acceleration spectrum. So here they have given the response spectrum, sorry. So here they have given the acceleration spectrum. So they're asking us to use this to find the following quantities. So first we need to find out the effective horizontal stiffness of the structure. So for this we need to use the concept of static condensation. So for this, let's write down the force displacement relationship for this whole frame. And we can also assume that all the members are axially rigid. So now in this, for this frame, we have 3 degrees of freedom, 2 rotations here and here, and also 1 displacement. Because the beam is also axially rigid, there's only 1 lateral displacement. So the force displacement relationship for this frame would be M1, M2 and P, where M1, M2 and P are the external moments and force acting at this degrees of freedom. So this is equal to K, which is the global stiffness matrix, multiplied by, we will write down the components of K, theta 1, theta 2 and delta. Delta is the displacement. So now let's write down the elements of this K matrix. So for this, we need to remember the stiffness coefficients for uh, different displacements. So for example, we have the standard stiffness coefficients when we apply a unit rotation. So for example, we have this thing and we apply a unit rotation by fixing all the degrees of freedom. A moment of 4 EI by L is generated at the near end and 2 EI by L is generated at the far end. And we also have the shear forces that are generated.
Yeah.
So those things we need to remember. So 6 EI by L square and 6 EI by L square will be generated. So using this thing, let's write down the components of this. So the first column corresponds to theta 1. So when theta 1 is applied, so the frame is going to deform like this. Okay, this is the positive convention that we are using. So we have the moments generated both near this column as well as at the beam. So this would be how much? Both are the near ends. So it would be 4 EI by this value is L by 2 and this is 4 EI by L. So this would be the first column, the first element would be the summation of these two. So we have 8 EI by L plus 4 EI by L. That would be totally 12 EI by L. And then the moment that is generated here would be 2 EI by L. Hence we have 2 EI by L. And the forces that are generated, the shear forces that are generated would be only for this column, it would be generated. So that would be like this in the direction that is opposing the moments. So that would be 6 EI by L by 2 the whole square. So this is in a direction that is opposite to the positive convention that we have assumed for the displacement. So this would be minus 24 EI by L square. So similarly for theta 2 we can write down. So if you write down for theta 2, so it would be like this, right? So the first element would be the moment corresponding to theta 1. So that is 2 EI by L. The second thing is summation of this and this, that would be 4 EI by L plus 4 EI by L because the length is same for both the beam and this column. So that would be 8 EI by L. And then the force, the shear force that is generated, that would be, so again the force will be in the opposite direction and here the length is L. So this would be minus 6 EI by L square. Okay, similarly we can write down for the displacement. So corresponding to the displacement degree of freedom. So we have so this is the unit displacement is applied. So in this case, what would be the moment? So moment would be opposing this and it is 6 CA by L square here and 6 CA by L by 2 the whole square here. So we have the two components as this is corresponding to theta 1, that is minus 24 EI by L square and this is minus 6 EI by L square. And corresponding to these two columns, we have a shear force here as well as here. So that would be, here we have 12 EI by L by 2 the whole cube, and 12 EI by L cube. So summation of these two things corresponding to this degree of freedom. So that would be 12 EI by L cube plus 12 EI by L by 2 the whole cube. So this is the whole stiffness matrix for this frame. So now let me just write it down here again. 12 EI by L and 2 EI by L minus 24 EI by L square, 2 EI by L and 8 EI by L minus 6 EI by L square minus 6 EI by L square, and this would be how much? So 12 8 is 96. 96 plus 12 would be 108. 108 EI by L cube. So this is our stiffness matrix. So in this thing, what we have to do is we have to find out the relation between theta 1, theta 2 and delta, and then we should find out K effective using that formula. So in the first session, we have seen this relation already. So we can write down M as a column vector consisting of both the moments, and K can be simplified as K can be written as K theta theta, K theta delta, and K delta theta and K delta delta. So here, so this part consisting of this first four elements, that is K theta theta matrix, and this part is K delta theta, and this part is K theta delta, and this element is K delta delta. So now we can simplify, we can find out the relation. So since we have no external moments M1 and M2, we can write down the relation theta is equal to, and so theta is again the column vector theta 1 and theta 2. So we have the relation K theta theta multiplied by the theta, sorry, this is for M. So we get for theta K theta theta inverse K theta delta multiplied by the delta. Okay, now we need to substitute and find out. So again for P we can write down P is the force, P is actually, so if you remember this K multiplied by theta 1, theta 2 and delta, this gives M1, M2 and P. So now for obtaining the lateral force P, we have to multiply this third row with this column. So this can be written in terms of these elements as K theta delta, K delta theta multiplied by this theta 1 and theta 2, right? So which is nothing but this thing, theta 1 and theta 2 plus this thing, which is k delta delta multiplied by delta. So now we already have the relation for theta in this equation. We have to substitute this here. So let's substitute. P is equal to k delta theta and theta is k theta theta inverse k theta delta. So it's actually minus k theta theta inverse. So minus k delta theta multiplied by this value plus k delta delta multiplied by delta. So we have P is equal to k delta delta minus k delta theta multiplied by k theta theta inverse k theta delta multiplied by the delta. Delta is a common, which is a scalar value. So now this is in the form of P is equal to k effective multiplied by delta. So which is what we need to find out, which is what is asked in the question. So determine the effective horizontal stiffness of the structure. So now we have all the values and we need to substitute in this big formula. So in this we know the k delta delta, k delta theta is known. So first let's find out this k theta theta inverse. So 8a by L. So what would be the inverse of this? So 1 by AD minus BC, that is so we have L by EI 1 by 92 times. So 8 minus 2 and 12. So we have the other values as well. So k delta delta is 108 EA by L cube and k delta theta is this row vector. So let's substitute all this in the k effective equation. EI by L cube minus, so k delta theta is this thing, so which is minus 24 EA by L square. So we have both the minuses, so that would become plus 24 EA by L square and 6 EA by L square So this is multiplied by k theta theta inverse, which is L by EVI multiplied by 1 by 92, 8 minus 2 minus 2, 12, and k theta delta is this column vector, which is minus 24 EI by L square and minus 6 EI by L square. So try to simplify this and tell me the value that you're getting, simplified expression that you're getting. So you can take out EI by L cube as common actually, and you'll have 108 plus, because this L by EI and L by EI would get cancelled, and you'll be left with 1 by L and 1 by L. So that you can take out as common, and you'll be having 24, 6, 1 by 92, 8 minus 2 minus 2, 12, and here you have minus 24 and minus 6. So what is the final value? Are you trying? So you would get a value of 59.48 EI by L cube. So this is the effective stiffness for this horizontal frame. So K effective is equal to 59.48 EI by L cube. So now they have given in the question the values of Young's modulus, length and other section properties. So using them, we need to find out the actual value because we need to find out other elemental forces as well. So now let's substitute for all the values. 59.48 multiplied by Young's modulus is given as 3 into 10 power 6 pounds per inch square, and the moment of inertia, the second moment of inertia, we need to find out. They have given that it's a square section, so that would be d power 4 by 12. So that means 10 power 4 divided by 12 multiplied by L cube. So L is given as 24 feet. So we need to convert this feet to inches because all the units of length are in inches. So we have 24 feet and 1 feet is 12 inches. So if you evaluate this or try to evaluate this, so you would get a value of 6224.73 pounds per inch. So this is the value of effective stiffness. So why do we need to find the value of effective stiffness? Because we need to find out the time period for this single degree of freedom system, so that from that we can find out the acceleration response, the pseudo acceleration response. Using that, we can find out the member forces which is required in the second part of the question. So now we know the effective stiffness and mass is also given. So using these things, we can find out the time period. So okay, I will write here. So time period Tm is equal to 2 pi square root of m by k. So 2 pi square root of, so let's see, mass is given as 26 pounds second square per inch. So it's already mass only. So we can directly substitute, which is 26 divided by 6224.73. So how much is the time period now? So this is 0.406 seconds. So using this time period, we can find out the acceleration response for this particular thing. So we got 0.406. So that means it should lie between 0.1 and zero point 0.5, and it has a constant value of 1. And this 1 means, so this is a ratio of the actual acceleration unto the acceleration due to gravity. So to get the actual acceleration, we must multiply this response value with respect to the, we must multiply this value with the acceleration due to gravity. So we are using this American unit, so it is 386 inch per second square. So we have the pseudo acceleration. Yeah, Prathamesh, you have any doubt?
Actually, I have a doubt in second problem.
Okay, yeah, yeah.
Could you once repeat how we calculated the moment?
So moment, so for example, we have the system like this, right?
Hmm?
So what else? So you have a storage tank, and then we have this mass, and we also have base here. So, so this we already know. That means, so for this thing to be in equilibrium, there must also have been an external force here. So I just found out the overturning moment with respect to the base, since we know the height of the structure. So
Okay, ma'am. So the 60 that we have taken is
the shear force,
okay.
which must also have been acting at the top because it's in equilibrium.
Correct. Yes.
Yeah,
Okay. Thank you.
yeah. So now we have inch per second square. So we know the pseudo acceleration, and the first thing is, so it has got two parts. First thing is find out the total base shear, and the second thing is shear at the base of short and long column separately we need to find out. So the total base shear would be K effective multiplied by the displacement, the maximum displacement, right? So base shear is equal to K effective multiplied by maximum displacement. So the pseudo acceleration is actually defined as omega n square, the maximum displacement. So we can find out the displacement. This is A divided by omega n square. And again, omega n is equal to 2 pi by Tn. So that would be 15.48 radians per second. And substituting here 15.48 square, that would be how much? 386 divided by 15.48, the whole square, 1.61 inches. So the base shear would be K effective, we have found out as 6224.73 multiplied by 1.61. So the base shear would be so this can be written as 10.02 kilopounds. And next we need to find out the base shear individually at both the columns. For this, let's first focus only on the short column. To find out the shears, we can find out first the end moments and then we can find out the shear from there. Now that we know theta, now that we know delta, we can find out the values of theta. Using the values of theta, we can find out these moments. From there, we can go and find the shear forces. So theta 1, theta 2 is equal to minus k theta theta inverse and k theta delta multiplied by delta. So this is equal to, so we can substitute all the values and it will be minus 1 by L, or else try to substitute here. So we have k theta theta inverse L by 92 EI minus 2 and 12. And k theta delta minus 24 EI by L square and minus 6 EI by L square multiplied by delta. So we have minus 1 by 92 L 8 minus 2 minus 2 12 and minus 24 and minus 6. Multiplied by 1.61. So evaluate this. Yes, sir. You have some doubt? Dr. G.R. Patil has raised hand. You have some doubt? So if you evaluate this, you'd get value of 3.1149 by L and 0.420 by L. So now we have the values for this theta 1 and theta 2. So we have beam and then we have column. So our whole structure would be displacing like this generally. So here we need to find out the moment. So this moment we can find out using the slope deflection equation. M1 is equal to 4 EI by L theta 1 plus 2 EI by L theta 2 for the beam. So the same moment would be acting here as well. So we can substitute for theta 1 and theta 2 as well as other quantities. So we have EI by L for uh, theta 1 is 3.149 by L plus 0.40 by L multiplied by 2. So that would be the E value and I value are already given. So let's substitute that. 3 into 10 power 6 multiplied by 10 power 4 by 12 multiplied by 13.436. So the total value for the moment would be 404.97 kips inch, kilopound inch. So now we got the moment at one end, which is 404.97, and here also we need to find out the moment. Again we can use the slope deflection equation. So m is equal to minus 6 ei delta by L square plus 2 ei by L theta 1. So if you substitute all the values, you would get a value of 784.99 kips inches. So now the shear forces must balance this unbalanced moment. So V short would be equal to 404.97 plus 784.99 divided by so 24 multiplied by 12 multiplied by 2. So this would be, because the length of the column is L by 2, that would be 24. So 2 goes up. So now we have the V short. The shear force in the short column would be 8.26 kips. So the total base shear must be the summation of base shear at the short column and the long column. So we know the total base shear. V total is equal to V short plus V long. So this is equal to the total base shear. We got it as 10.02 kips. 10.02 is equal to 8.26 plus V long, which means V long is equal to 1.78 kips. So this is the final answer for this question. So need to erase these things. I'll try to upload this solution in the document in the folder which is already shared in the website. Moving on to the problem number 4. A one-story building idealized as a 12 feet high frame with 2 columns hinged at the base and a rigid beam has a natural period of 0.5 seconds. Each column is an American standard wide flanged steel section. So W8 by 18. Its properties for bending about its major axis or Ix is equal to 61.9 inch power 4. and the section modulus is given as 15.2 inch cube, and the Young's modulus is 30,000 kilopound per square inch. Now, neglecting um, neglecting damping, determine the maximum response of this frame due to a rectangular pulse force of amplitude 4 kips and duration Td is equal to zero point 0.2 seconds. The response quantities of interest are displacement at the top of the frame and maximum bending stress in the columns. So now we have a frame, portal frame again. So this time the beam is rigid. So the calculation of the effective stiffness would be relatively simple compared to the previous problem. So we have, so there is a rectangular pulse with amplitude 4 kips and acting for a duration of 0.2 seconds. So now we need to find out the maximum displacement and everything. So we can directly use the standard result for this problem. Uh, so let's first find out Tn. So when we know the relative values of Td and Tn, then we can find out the expression that is appropriate for finding out the maximum displacement. So they have already given Tn, which is 0.5 seconds, and Td is equal to 0.2. So for this case, the maximum response factor is given as 2 sine pi Td by Tn, which is equal to 2 sine uh, Td by Tn is equal to 0.2 by 0.5. So that would be 0.4. So now we have 0.4 times pi. So if you evaluate this thing, you would get a value of 1.902. Now we need to find out the maximum displacement. For that we have to find out UST0. UST0 is equal to P naught by K. In this case, K effective because we have a portal frame. So they have given that the beam is rigid. That means the effective lateral stiffness for this frame would be simply summation of the stiffness coefficients for the two columns when a unit lateral displacement is applied. So when a unit lateral displacement is applied and the forends, here the forends are hinged. So in this case actually, so the unit displacement when you apply the value of the, so the shear force that would be produced is 3 EI by L cube. So here we have two columns. So the total K effective would be 6 EA by L cube. So E is given as 30,000 multiplied by I is 61.9 divided by L cube. The length is 12 inches. So this is actually in feet, 12 feet. So we must convert this to inches, whole cube. So after evaluating, this gives a value of 1.865 kips per inch. Sorry, this would be 3.73 kips per inch. So that means UST0 would be P naught is given as 4 kips, 4 by 3.73. So that is 1.07 inches. So the maximum dynamic deformation displacement at the top of the frame U0 would be RD times UST0. So that is 1.902 multiplied by 1.07. That would be 2.04 inches. So this is the first part. The second part is maximum bending stress in the columns. So for this we need to find out the moments in the column. From there we can find out using the simple bending theory the maximum bending stresses. So here the bending moment is generated mainly because of the displacement that is applied at the top. Since the beam is rigid, there won't be any rotational degrees of freedom for these elements. So in this case, when a unit displacement is applied, there would be a anti-clockwise rotation, anti-clockwise moment that is generated with a magnitude of 3 EI by L square. This is for unit displacement. For a displacement of some value, so that would be 3 by L square multiplied by the displacement. Hence, the moment that is generated in the columns would be so that would be 3 multiplied by 30,000 multiplied by 61.9 divided by 12 multiplied by 12 the whole square multiplied by 2.04. So that would be 548.07 Gibbs inch. This is the moment that is generated. And we know using the simple bending theory that maximum bending stress would occur at the top layer of this section. So this is actually an I section, and they said that the bending is going to happen about the major axis. And we know the relation between the stress and the moment. The bending stress is equal to m by z, where z is the section modulus. So 548.07 divided by the section modulus is 15.2 inch cube. So this would give a value of 36.06 KSI. So these are the two parts of the question. One is the maximum displacement at the top of the frame, and the other thing is the maximum bending stress in the columns. So here we have used this expression because we have TD value which is less than the natural time period. So if the natural time period, if the TD value is at least like half of the time period, then the maximum displacement factor would be simply 2. So since it's very small, the maximum displacement occurred during the free vibration phase. So this expression is valid for the free vibration case. So this is for free vibration maximum value. So that is RD is equal to 2 when TD is, so TD by Tn is greater than 0.5, 2 sine by TD by Tn when TD by Tn is less than 0.5. So this is the reason why we have used this expression. Okay. Moving to the last problem of this session. So again we have a steel frame shown in figure is subjected to a horizontal force applied at the girder level. The force decreases linearly from 5 kips at time t is equal to 0 to 0 at time t is equal to 0.6 seconds. Determine the horizontal deflection at t is equal to 0.5 seconds. Assume the columns are massless and the girder rigid. Neglect damping. So this situation is similar to the previous situation, except that we have a different kind of pulse which is not standard. We have a pulse of this kind. So at time t is equal to 0, we have 5 kips, and at time t is equal to 0.6 seconds, the force has linearly dropped to 0. So for this kind of pulse, we need to find out the horizontal deflection, that is the displacement at time t is equal to 0.5 seconds. That means first we need to find out the forced vibration response for this case. So for this, first let's write down the equation of the force description for this problem. So it can be simply written as P of t is equal to, using the equation of line method, we can write this down, 5 minus 5 by 0.6 times t. So that would be 5 minus 8.33 t. So they have given that we can neglect damping, which means the Duhamel's integral for this thing would be u of t is equal to integral 0 to t p of tau sine omega n t minus tau d tau. So if we evaluate this, integral 0 to t 5 minus 8.33 tau multiplied by sine omega n t minus tau d tau. So this is equal to we have 5 by omega n cos omega n t minus tau between 0 to t plus so it's actually 1 by m omega n. So here we have m omega n square. So that would give k value here. So the second thing is integral 0 to t minus 8.33 tau sine omega n t minus tau d tau. So this is equal to evaluating this second component. So this is equal to 8.33 tau cos omega n t minus tau by omega n minus integral 0 to t cos omega n t minus tau by omega n d tau. So this is between the limits 0 to t. So this whole thing is multiplied by 8.33. So this is equal to 8.33 so we have um, so if you substitute, if you apply the limits, we get t by omega n minus, so here we have plus sine omega n t minus tau by omega n square between the limits 0 to t. So this would be totally 8.33 t by omega n plus sine omega n t by omega n square. So this is the lower limit, so we have minus here. The total response is u of t is equal to between the limits t to 0 we have here 5 by k 1 minus so 0, so that would be cos omega n t. So u of t would be 5 by k 1 minus cos omega n t, and then so here we have minus, so bringing that inside, so this would become plus 8.33 divided by m omega n squared sine omega n t by omega n minus t. So this is the total response for this kind of pulse. So now we need to find out um, so this is so we need to find out the response or the horizontal deflection at a time t is equal to 0.5 seconds. For that, first we need to find out the value of k effective. So in this case also, there is a portal frame with unequal column heights, but again, uh, it is given that the girder is rigid. That means the only degree of freedom is the horizontal displacement. Hence, the effective stiffness would be the sum of the stiffness coefficients because of the horizontal displacement, the unit horizontal displacement at both the columns. So in this case, we have one of the columns as fixed and another of the columns as pinned. So the total effective stiffness So for the fixed case, it would be 12 EI by L1 cube, and for the pinned case, we have seen in the previous example, it is 3 EI by L2 cube. So, and also for this sections, we have in the question it is given E is equal to 30 into 10 power 6, and then I value is 82.8 inch power 4. So for this, let's substitute the values. So 12 multiplied by 30, 10 power 6 multiplied by I is 82.8, and L1 is 15 feet. So that would be 15 multiplied by 12 the whole cube plus 3 multiplied by 30 into 10 power 6 multiplied by, both the sections are same. So we have the same second moment of inertia divided by, so this is 15 plus 5 feet. So that is 20 feet multiplied by 12 the whole cube. So the effective lateral stiffness would be 12 multiplied by 30. This is 5111.1 plus 82.8 divided by 20. 539.06. So the total effective stiffness is 5650.16. Pounds per inches. This is the K value, and we also need to find out the angular frequency omega n. So the mass is given as, so it's actually the weight is given as 20 kips, that means 20,000 pounds. So omega n is equal to square root of K divided by W by G. So this is equal to square root of K is 5650. So 5650.16 multiplied by G is 386 divided by W is 20,000. So 20 multiplied by 10 cube. So this would give a total value of 10.44 radians per second. Omega n is equal to. So now we have all the values. So we need to find out the response at 0.5 seconds. So U of 0.5 is equal to 5 by K K is 5650. 0.1 6 1 minus cos 10.44 multiplied by 0.5 plus 8.33. M omega n square is nothing but K. So we have 5650.16 multiplied by sine of 10.44 multiplied by 0.5 divided by omega n is 10.44 minus 0.5. So this is 0.4 mm plus it is in inches. So force is also in kips. So it's actually into 10 power 3. Once you evaluate, you get a value of minus 0.4072 inches. So this is the value of displacement at 0.5 seconds. So this equation we were able to use because it is still in the range of the application of the force. That is, the time is less than Td. If T had been greater than Td, we need to find out the response for the free vibration case and use that equation for finding out the displacement response. So this is the today's problem solving session.